Okay, let's talk section 6.3, relative acceleration. Now, what we can do, let's start at the beginning. If we have a van, and I'm standing in the back of my van, I drop a ball for whatever reason, right, let's just say I'm going for a walk actually, and if there's another observer here watching me, then in theory I should be adding up my acceleration of me and my acceleration of the van, and that will work out my total acceleration. But let's start off in the case of an inertial frame. So basically acceleration of the observer compared to the ground, or me compared to the ground, is going to be equal the observer of the van relative to the ground. Let's not worry about this guy for a sec. Plus the acceleration of me relative to the van. So acceleration of me relative to the ground, so we'll put a tree in here to represent the ground. So the acceleration of me compared to that tree is going to equal the acceleration of the van plus the acceleration of me. Does it? Now hopefully that seems reasonable. But let's do the trivial case, or the initial case. For an inertial frame, so we're going to say that the van is in an inertial frame. And remember, the big thing about an inertial frame is there is no acceleration. Cool. So that means so for the above equation, for above, observer, not A, equals 0. So for an inertial frame, when the van is not moving, we can say that AOG, the acceleration of me relative to the ground, or the tree in this case, is going to equal the acceleration of the van compared to the tree, which equals 0, plus my acceleration, A, of the observer relative to the van. So basically that says that the acceleration of that whole system is just going to be me, because the van's not moving. And this actually will give us that the force of the observer to the ground is also equal to the force of the observer to the van. So that means everything's cool. Force, Newton's laws are obeyed. Life is good. So let's now, okay, what we're going to do is we're going to take the next case, which is accelerating frames of reference. Remember, so now we are in accelerating frames of reference. And so now we've got a slightly different case. We're still going to use this. Let's take an example. We'll take example 6.2 in the notes. And remember what we were saying before, that in an inertial frame, all of Newton's laws have to hold true. So, in the case of an inertial frame, the laws look the same to both of us. However, what about if we're accelerating? So I'm in the van, and I'm there with the ball. And if I drop the ball, what happens? Well, if there's somebody on the outside, so we've got the van accelerating. So this is example 6.2, just out of interest. What does this observer see? Well, the observer sees the ball carry on at its initial velocity and drops down. So if the van was moving along and is accelerating, that ball will retain the velocity of the van at the instant it was dropped, but it won't retain it after it's dropped. So this ball will continue along at the same velocity that it had when the person dropped the ball. But what about to the person in the van? Well, what's happening is, while the ball's got the same velocity, this person's actually picking up speed. And what actually happens to what the person inside the van sees is this person sees the ball do this. And you'll notice that this person and this person are seeing two totally different things happening. And why is that? That's because this frame of reference is accelerating. This is non-inertial. So to the person inside here, if this was a constant speed, they dropped the ball, they just see the ball do this. If the van was not accelerating, this person would see the ball do this. But because the van is accelerating, they see it do it that. The only reason it would do that normally would be because there's a force causing the ball to accelerate. And what we actually call that, so what we call that a virtual force. So a virtual force only exists inside an accelerating frame. So yeah, so let's actually try this. Let's try and put this together and let's change that equation. Remember we had our equation up there. Where's our equation from before? So we're going to have, with respect to the inertial system, and in this case the inertial system is going to be this person here. Force of the so let's say that the van has got acceleration ASG, so A of the van compared to the tree. We'll call that just big A because we can. So the force here of the observer, that the observer in the system sees, so this is the force that I'm seeing, equals the force of the observer with respect to the ground, so basically minus the mass times the acceleration of the system with respect to the ground, so with respect of the van to the ground, which I know is horrible, but we'll do a couple of examples with this in a second. There's too many FOs and S's and FOGs and blah. But what we'll do is we'll apply this in a second to elevators. Why? Because Einstein loved elevators when he was thinking about this type of stuff.